Section 2.1, continued, part 3. We're looking at standard unit vectors in this video. Standard unit vectors for plane vectors. Remember, those are vectors that exist in the plane. They only have 2 dimensions. We have 2 standard unit vectors. One of them is I hat. The other one is J hat. I hat is the standard unit vector that points in the direction of the positive x-axis. It's exactly 1 unit long, which is why we have a hat on it and why we're calling it a standard unit vector. J hat points along the positive y direction. Again, it's 1 unit long, which is why we're calling it a standard unit vector. These 2 vectors are used to make any other vector you could imagine in the xy plane. And when we use these 2 vectors to write one of those other vectors that we create, we call it a linear combination of the standard unit vectors. This is a really long phrase. If you're taking linear algebra, you're going to see this a lot, so you're kind of lucky that you'll have that material solidified in another class as well. But it's a long phrase that just means use the I hat, J hat notation. That's all. It's a pretty cool shortcut. If you know the components of your vector v, you're just going to take the x component, which I'm going to call v1, and you're going to put that as a coefficient on the I hat standard unit vector. Then the y component of our vector v, we'll call that v2. We'll put that as a coefficient on the j hat standard unit vector. And if we put a plus sign between them, that's what we're calling a linear combination of the standard unit vectors. Using these standard unit vectors is pretty straightforward if you already have the components for your vector. For example, the vector w has the components 3 and -4. I'm going to take the 3 and write it as if it's a coefficient on the I hat unit vector. And then I'm going to add that to the -4 as a coefficient on the j hat unit vector. So the vector w can be written in either one of these 2 ways. Now let's pause for a second and appreciate that this might be brand new notation for some of us, and it's easy to get these things mixed up. One common mistake: using both the I hat, J hat notation and the pointy brackets. So these are things we do not want to do. Don't use a pointy bracket and then do 3I hat plus -4J hat. Not good. Another common mistake: we don't want to use the I hats and the J hats with a comma between them, because the plus sign is what's combining the 2 things. In the I hat, J hat notation, we don't need the comma. So these 2 things together, they don't belong together. I think that's pretty much it. Using the pointy brackets and the standard unit vectors together is a big no-no. So remember that we have 2 different notations here. One is the component form, and then the other one is the unit vector form, which we can say that the long way: linear combination of standard unit vectors. For short, I'll just say the unit vector form. So let's try not to mush those together and create a whole new notation. We don't need that. Now, I said it's easy to use these standard unit vectors when we already know the components of the vector. It's less easy, not that it's hard, but it's less easy if we're given the components of a vector u in terms of an angle and a magnitude. So in this second problem, we know a couple of things. One, we know that u is a unit vector, which tells us the magnitude of u is 1. 2, we know that the unit vector forms an angle of 60 degrees with the positive x-axis. So if we wanted to visualize that, we could say rotate 60 degrees. Here's our vector u. This is where trig comes into play. Remember that the components for this vector u are going to be magnitude, which is 1, times cosine of the angle 60 degrees for the x component. And then for the y component, that's going to look like 1 times sine of 60 degrees. Another short way to use these component forms is to say u hat is equal to the magnitude of u times the vector, the direction vector, cosine 60 sine 60. So the cosine and sine components make up a unit vector, like a direction vector. And then the magnitude just goes out front. In this case, our magnitude was 1, so we would just write 1 times cosine 60 sine 60. But hopefully we know some of these short algebra expressions, trig expressions. Cosine of 60 degrees, sine of 60 degrees. If we don't know those, we can type them in on our calculator. But if we do know those, we can plug them in real quick. I can take a second to show you a quick shortcut that helps me remember these angles. There's a few special angles. There's 0 degree angle, that one's special. We also have the 30, 45, 60, and 90 degree angles. These are all pretty special because we have exact values for our trig functions that correspond to these angles. Special triangles come to mind as well. We also note we have these two trig functions, sine and cosine, that we use often. So I make this table. I put all of the 5 special angles in quadrant 1, including the angles on the x-axis and the y-axis. Then I make a row for my sine. I make a row for my cosine. Now watch how I make this table. I'm going to start by numbering from 0 to 4 in the sine row, and then I'm going to reverse that in cosine. Then I'm going to go through and take the square root of each value. And after I've done this, I'm going to divide each number by 2. Some of these will simplify. For example, the square root of 0 is 0. 0 divided by 2 is 0. Square root of 1 is just 1, so I could write this one as 1/2. Root 2 over 2, that's as simple as it gets. Same for root 3 over 2. Root 4 over 2, that's like 2 divided by 2, or 1. And I can do the same thing in these bottom rows. These are the trig values at these special angles. For example, sine at 60 degrees is root 3 over 2, and it's already rationalized for you. You're welcome. Cosine at 60 degrees, that is 1/2. And we're done. Not too bad, right? Let's get a little more practice using these standard unit vectors. We're given a vector A, and then we're also given the description for a vector B. We're asked to express A and B in terms of standard unit vectors. So let's start off with A. The vector A has components 16 and -11. This is the easy one, right? Just use those components as coefficients on the I and j unit vectors. Now, if j has a negative component to it, we don't have to write plus -11 j hat. We can just write -11 j hat, and we're done. All right, that one's done. Next, we need to do B. We know that the vector B is a unit vector, so our magnitude is 1. And then we're given the angle 225 degrees with the positive x-axis. So I'm going to pop that into the cosine and sine component. Now from here, you can use your calculator, or you can try to find a corresponding angle with 225 degrees. To do that, first you might need to think about where is 225 degrees. I know it's more than 180, but it's less than 270, so it's probably somewhere in quadrant 3. If I wanted to find a corresponding angle, I need to form a perpendicular with the x-axis. So I need to find this angle. To do that, I can do 225 minus 180, and that would give me 45 degrees. So that means I can use the cosine and sine values that correspond to a 45-degree angle in quadrant 1. The only thing I might have to adjust is the sign, a plus or a minus. Maybe you've seen this cute shortcut before. All students take calculus. It's a short way to remember that every trig function in quadrant 1 is positive, which is why we have an A for all. Only sine is positive in quadrant 2. Cosine and tangent, those are negative in quadrant 2 because of the x values being negative. In quadrant 3, tangent is the only trig function that's positive. That's because sine and cosine are both negative. X and y are both negative in quadrant 3. And then in quadrant 4, cosine is the only positive trig function. So we can use this all students take calculus to help us remember if we need to adjust by a positive or a negative. For example, I found that a 45-degree angle is corresponding with the 225-degree angle that we're given, which means I could really look at this as if it were an angle in quadrant 1. I could find the sine and cosine values of the 45-degree angle, but then I need to think about whether or not I need to adjust by a negative. Now maybe you don't have sine and cosine memorized for quadrant 3, but maybe you do have them memorized for quadrant 1. So if I had written instead of cosine 225, if we had cosine 45, maybe you'd say, oh, I know that one. But remember, we're not at cosine 45. We're similar to it with maybe a negative. If we look in quadrant 3, we know cosine is negative. So negative times cosine 45 is equal to cosine 225. Similar for the sine function, sine at 225, we could use the corresponding angle of 45 degrees, but then looking in quadrant 3, we know that sine is negative, so we would need to adjust this by a negative sign. So for our final answer, this vector would look like negative root 2 over 2, negative root 2 over 2. Those are the components. Remember, we need to write this in terms of standard unit vectors. So our final answer for B would look like negative root 2 over 2 I hat minus root 2 over 2 j hat.